the recording session. So I'm going to go back here to, oh, where's my PowerPoint? There it is. Okay, so for this PowerPoint, you're asking about the questions, right? So let me skip over all of this. Okay, we did something similar to this before, right? But this one is slightly different. Okay. So what I'm going to do here is, yeah, we left off with this question number 16 or slide number 16. I had gone over this part here. I won't go over this part. You guys can read that. With the open-end manometer, there is a question that goes with this part here. So what I'm going to do, I won't work the question here because I actually do have a question on my iPad. Slides. So I have some questions there. But what I'm going to mention is you want to know how to figure out the pressure in an open-end manometer. So a manometer is, as it says here, usually devices in the lab, old school devices in the lab have the term meter in them to say it measures something. And so in this case, the manometer measures the pressure of the gas that's produced versus the barometer measures the pressure of the atmosphere. So this one here, it says, is a non-mechanical instrument used for measuring pressure. So when you're making gas in the lab, the gas has to be enclosed in a container, or else, it will just spread in the room and fill the whole room, and then you will lose the gas you just made. So once the gas is made, it's enclosed in the container, and then the pressure is measured. And the pressure of the gas is similar to the concentration or the amount. If you want to know how much gas you made, you measure the pressure. So what we're going to try to do here in figuring out the pressure is we'll consider these three measurements. Ooh, where's the draw feature? Yeah, we'll consider these three measurements right here. The enclosed gas pressure, and we're told here the enclosed gas pushes on one side of the column of mercury. You have the atmospheric pressure pushing on the other side. So I will show you the manometer so you can see where these gases are acting. The enclosed gas, the atmospheric gas, and then the difference in the pressure here. Okay, so with that, we can figure out the pressure of the gas. So there's a picture right here that shows you how to actually work this out. Okay, so my plan today is I start with this part here. I do have a worksheet on my iPad, which is on QuickTime Player. We'll go there. But for us to figure out the equation for the open-end manometer, they give you an equation here. But with this section, the equation is not so simple. Let me make this a little bigger. It's not so simple. The equation is not something that you memorize. I realize as a student, the equation is something that you derive based on the situation or the picture given to you. So what I mean by that is you actually kind of look at the pressure going on. So there's three pressures that you're looking at in this picture. I will start with the image on the left. Okay. The one pressure is the pressure from the gas. So here they made the gas kind of greenish color so you can see where it's being made. Inside this container, we have a gas being made. From the gas, there is a pressure. This pressure is called the pressure from the gas. So the symbol is P sub gas, or they have it here as P sub G. Okay. And then the gas, once it's made in the chemical reaction somewhere in here, some chemicals reacted, they made the gas. The gas then travels up here through this column all the way here. It's trapped, it has nowhere to go. So it travels all the way here and it runs into this U-shaped tube, or it looks like a J-shaped tube. Anyway, you have that tube right there where the tube is usually filled with mercury. Before the tube was connected here, it looked more like this. So it's not exactly U, it's a little bit more than that, at least the one that we're seeing here, like this. But it had mercury that was the same level on both sides, right? Same height from the center on both sides. One end of this tube is open, so they call it the open end manometer. The other end is connected to this part right here. So this one here connects to the gas. So before you actually connect it to the gas, or the container making the gas, the mercury has the same height. When the mercury has the same height, the pressure that's made from the height difference is zero. But once you connect it, look what happens. The gas that's being formed, it travels and travels and travels, but it begins to push on one end of the mercury column. And so it pushes down. So this column here, before it got connected, may have been around this height right here. Once it got connected, it got pushed down by the gas. Then the other side that was here, also the same level, got pushed up. Okay? So now we end up having three pressures. The pressure from the gas is coming from the container and pushing down here. Since this other end is open to the atmosphere, there is air coming from the atmosphere pushing down here and causing a pressure from the atmosphere called PA. Okay? Sometimes this is called PATM, but the idea is pressure from the atmosphere. And then you have a difference in height. The difference in the height creates another pressure that's called pressure due to the height. Here, the abbreviated PHG. So let me go ahead and summarize that before we continue. We now have three pressures acting. And the question you ask yourself in this section is here is how are these three pressures related to each other? So you have a pressure G, which is the pressure from the gas. So I'll call this gas pressure.
I'm sorry, is the pressure from the height PHG, is that basically like gravity's pull?
I it's different from that because if you're bringing in gravity's pull, then you're talking about what is it called? The weight, right? The pressure due to the height is not really. You're talking about the pressure due to gravity?
Yeah, is it the same as the PHG?
Yeah, no, this is slightly different. This is the pressure that is generated only when there's a height difference. When there is no height difference, there's no pressure due to height. But with gravity, there's always gravity all the time. We're always experiencing gravity. Right. So when you're saying the pressure due to gravity, I don't think I understand what you're asking exactly. Have you had a physics class?
No.
Okay. I see. Okay, yeah. So when you have a difference in sometimes when you have a difference in liquid level, you have a difference in height, like if you're standing on top of a ramp versus the bottom, that usually creates some kind of difference in potential or difference in height measurements and things like that. So that creates a difference. In this case here, it's the height difference that's generating that potential difference or difference due to height. When there is no height difference, there is no potential difference. So I'm trying not to go beyond the level of this class, right? Or what we're trying to cover right now. So when the heights are level, there is no height difference. When the heights are different, there is that height difference that generates the pressure. Okay, and that pressure sometimes due to the height difference can cause a flow to happen. Kind of like if you're trying to get a ball to roll down a ramp, the ball will roll down the ramp because one side of the ramp is high, the other side is low. You have a height difference. Okay, so it's something kind of like that. Only we're not going into the energy difference and all that stuff. We're just sticking with the pressure difference here. Okay, so you have a pressure of a gas, you have a pressure of the atmosphere, PA equal pressure of the atmosphere. But I'm gonna double check on the pressure due to height to make sure because gravity is not really making a big difference in what we're talking about right now. We're talking about more of a competing pressures versus the effect of gravity. But I will double check just to make sure that it doesn't really influence this. So we have pressure of atmosphere, pressure of gas, and then we have what was it? Pressure due to height, right? Oh no, what have I done? Okay, I think yeah, pressure due to height. I think I'm going to the picture here, so it's making a difference in what I can write. Okay, so you see it, right? Anyway, the question you have to ask yourself, you have two pressures competing, pressure atmosphere, pressure gas. Which one is larger? The pressure due to height tends to go with the smaller pressure or the weaker pressure. Okay? So what I mean by that is the pressure of the gas is pushing more on the left side of the column versus the pressure of the atmosphere. The pressure of the atmosphere compared to the gas is weaker. For that reason, this setup here produces an equation that looks like this. Oh, I see why I can't write. It's because of where this picture is. Okay, so the pressure of the gas is the bigger and the heavier pressure of the two. So you write that by itself on the left side, then you add the two other weaker pressures, which is pressure due to height and pressure due to atmosphere. There. I'll just write that PG, PH, PA. So the two weaker ones are added together and they equal the stronger one. So you're always trying to see the two sides that are competing. Okay? And then on the right, we have a picture similar to the left, but this time, if you look at it, the side from the gas is the one that's higher. The side from the atmosphere is the one that's lower. So that tells you the side from the gas is essentially not being pushed down as much by the gas. So the pressure of the gas compared to the pressure of the atmosphere is not that high, right? If it was higher, then this would be pushing down like the scenario we have on the left. Over here, the pressure of the gas is the weaker one. So for your equation, you will write pressure of the atmosphere by itself because it's the stronger one of the two. It's pushing down more on the liquid mercury. You will write it by itself, then you add the other two pressures. Pressure of the gas plus pressure due to the mercury. Okay? Now they wanted to solve for pressure of gas. So once you have the pressure of the gas by itself, pressure of the gas equal pressure of A minus pressure of height. Okay. So we'll come back to this. I mean, we're going to be practicing some problems here. We'll come back and then we'll look at the active exercise problems. I'm going to go to the manometer slide that I have ready on this right here. Come on. Oh, this is a worksheet that I found online somewhere. So this gives us a chance to practice some manometer problems. So we have scenarios here. Actually, now that I think about it, I should have copied the other page, but that's okay. I didn't want us to spend the whole time on this page. On this one here, you have two pressures once again. You have picture A, picture B, picture C, picture D. So we have to answer the questions based on the pictures that they give us. Let me see if this is the biggest I can make this. Okay. So it says, show all calculation steps in the blank space following each problem. Round the answers to the correct number of significant figures. Box your final answers. Okay. The mercury Hg column in diagram A are of equal height. Oh, okay. So diagram A, remember, the pressure coming from here is the gas pressure, right? So I'll call that Pg. Pressure coming from here is the atmospheric pressure. I'll call that Pa. And then if there was a difference in height, that would be pH. So pH and Pg are of equal height. That's what they say, right? If the pressure of the confined gas is 749 millimeters of mercury, what is the atmospheric pressure in millimeters of mercury? So in this picture here, Pg, pressure of gas, equal Pa plus pH. Actually, I could put the pH anywhere. It doesn't make a difference because it technically doesn't really even apply here, right? You can see that the pressure of the gas and the pressure of the atmosphere are the same because they have equal height. So we are equating the height to the pressure. That's when you're asking me about the gravity. I'm like, no, we're equating the height here to the pressure, right? So essentially, pH equals 0. So then we conclude what they said, Pg equal Pa. So telling you the pressure of the gas is equal to Pg is equal to 749 millimeters of mercury. If that's the case, what is Pa? So what do you think P of A, the atmospheric pressure, is in millimeters of mercury? What do you think it is?
Is it the same because they're equal?
Mm-hmm. Yeah, it's the same because they're equal. So Pg is equal to 749 millimeters of mercury. Yeah, because they're equal. Exactly. Okay. So yeah, I feel like by the time we're done with at least four, you see how it works out. So remember, the equation is not something that you're memorizing. It's based on the picture, right? Next one, number two. Number two is based on picture B, diagram B. The difference in the height of mercury column in diagram B is 17 millimeters of mercury. Okay, so the difference in the height are right here. Remember, the pressure of the height is equal to the height difference. So that's saying that P of H is 17 millimeters of mercury. If the atmospheric pressure, so we're told PA is 769 millimeters of mercury, I'm right here. What is the pressure of the confined gas in mercury? What is Pg in millimeters of mercury? Okay, once again, the height relates to the pressure. So now I have to find out. I don't know my equation. The equation is based on the picture. So let's see. I have to zoom this in here to see this very well, right? Which is bigger, Pg, which is right here, or Pa, which is pushing down more on the liquid? Oh, I said Pg and Pg, right? I meant Pg and Pa. Which one do you think is bigger, Pg or Pa?
PG
Or
pushing
strong?
down more.
Pg. Yes. Pg is stronger, so it's pushing down more, right? So if it's pushing down more, then that means that it's got a higher it's a higher pressure, right? As a higher pressure, I write it by itself. Pg equal pH, the difference, plus Pa. So we add the weak ones together, right? Or the smaller ones together. Okay, so now that I know the equation from the picture, I can now use it here. Pg equal pH plus Pa. So I'm looking for Pg. pH is 17 millimeters of mercury plus 769 millimeters of mercury. That's it. See, these questions are not that bad, but if you have no idea what you're doing, then it seems like it's really bad. 769. Just remember, do not just memorize the formula. You have to know how to get it, right? How to figure it out from the picture. 786 millimeters of mercury. Okay, number three. The difference in heights of mercury column is 26 millimeters of mercury in diagram C. So again, P of H is 26 millimeters of mercury. So I'm right here in diagram C. If the pressure of the confined gas, Pg, is 741 millimeters of mercury. Okay, so I'm right here. What is the atmospheric pressure? What is Pa? Okay, so let me go back again, figure out what the equation is. So now I'm working on C. When I look at C, I'm competing Pa with Pg, and you can see Pa is stronger than Pg, right? Because it's pushing down more on it. So Pa will be written by itself equal Pg plus pH. Okay, so right here, Pa is equal to Pg plus pH. So yeah, you continue like that, 741 millimeters of mercury plus 26 millimeters of mercury, and you get Pa. So let's see this one here, 741 plus 26, 767 millimeters of mercury. So we have one last one, and then we'll move on from this concept. If the pressure of the confined gas in diagram D is so we have the pressure of the confined gas in diagram D, Pg is 811 millimeters of mercury, some right here, and the atmospheric pressure is Pa is 763 millimeters of mercury. By default, we're looking for pH, right? Two M's, Hg. We're trying to solve for this. What is the difference in height of the mercury column, right? These questions, in torr, different unit. Let me erase that. I made assumptions. In torr, right? Let me make sure that everyone's were in the same. Okay, the other ones were the same unit. They were in a different unit. Okay, so for this one here, once again, they're usually giving you two and asking you for one, right? So let's see. We got Pg, we got Pa. Let's see what the equation is. Okay, so G is bigger than A. P gas is bigger than Pa. So P gas is going to be equal to Pa plus pH, right? Because the gas is bigger. So P gas is by itself. I'm going to write this down here. P gas is equal to Pa plus pH. We're trying to solve for pH. So pH is equal to Pg minus Pa. So Pg, let's see, is 811 millimeters of mercury minus 763 millimeters of mercury. The pressure has to be positive because the height can't be a negative. You can't have a negative height. If you have a negative height, you rearrange it wrong. 811 minus 763, and that gives us 48 millimeters of mercury is pH. But they said write your answer in torr. So this is where you have to go back to the equalities I gave you on Tuesday that said 1 torr equal 1 millimeter of mercury, and you convert that. 1 torr equal 1 millimeter of mercury. So take your answer and then just rewrite it again with a different unit, 48 torr. So they could ask you, they said put your answers in little boxes, right? I forgot that part. They could, they could have you convert it to any unit they want in pressure. But, yeah. So we worked on this one page. Do you have any questions about this?
No, that's pretty simple.
Straightforward, huh?
Yeah.
Okay. Let me leave this thing right here, and then I'll continue with this slide. Okay, so in this one here, back to the PowerPoint slide, they say the pressure inside a steam boiler is 1427 psi. Express this pressure in atmospheres. Okay, even though it's worked on the left, let me go ahead and draw this. So this is not my iPad, so I'm writing with my mouse. It's gonna be a little wonky, my handwriting. So you always start with, in the dimensional analysis or calculation, if you don't know a formula, you want to start with dimensional analysis. Write your given first, 1427 psi. Then you want to go to your conversion table if you have one, or if you have a set of conversions. Remember I told you guys to either print a table down or write it down somewhere so you have a place to refer to. It makes it easier for you. So we're going from this, from psi to atmospheres. Now the conversion for this is normally 1 atmospheres equal 14.7 psi. Right? So just like we did before, PSI is here. PSI, you want to put PSI down here. So the number that goes with PSI is 14.7. And then this goes with 1 atmosphere, 1 atm. Okay, psi, divide this 2. I think they did that and they got, let's see, to confirm their answer, 1427 divided by 14.7. Yep, same thing. 97, ooh, 0.07 ATM. It's a lot harder to write with your mouse. But yep, that's it for that one. And then let's go see the other question. Okay. With this question here, okay, they want you to get the absolute pressure. Let's see. How would you report the absolute pressure in the tire? Okay, the absolute pressure had to have been defined before because we have 2 pressures here. The automobile pressure, and then we have the barometric pressure. Okay, so all you're doing is just converting the pressures and adding the 2. As far as our assignments are concerned, we're not going to be trying to figure out the absolute pressure. So what I can do is, for the sake of the question, since it's right here, I'll just do the conversion so we can have practice doing the conversion, right? But as far as this is concerned, actually, let me see. I just remember the other parts I want to go to here that have to do with the gas laws. So I'll just go over one of these real quick, and then the other one will be implied, because I want to make sure that we go over the gas laws so you can have practice with those problems, okay? Because I remember you guys have a deadline coming up soon. Okay, so with this one here, the absolute pressure that you're being asked to get is the sum of these 2 numbers, right? And when you convert these to PSI, sorry, they're given to you in PSI, you have to convert them to kilopascals. Okay, I was trying to figure out why you couldn't add them. I see now. They're in different units. This is PSI. So for this first one, you're going from PSI. Oh, that means I can't just do one. I have to do both. Okay. You have to go from PSI to kilopascals. The easiest way to do that is to do it through atmospheres, right? So let me do this. I see the issue now. This is not, let me see if I can write this out on my sheet of paper here, because so okay, so we're dealing with 2 conversions, 29 psi, and the other one is 30.09 inches of mercury. So let me delete this here. I'll write on my iPad. We'll have this here. I'll come back to it. Oops. Okay. And so the goal is for us to go to kilopascals in both of them. So the conversions we had Tuesday, was 1 atmosphere equal 14.7 psi, right? Then 1 atmosphere equal 101 point, I think was 325 kilopascals. And then 1 atmosphere, trying to think, 760 millimeters of mercury. Okay, so I think this is what I gave you guys last time we met, which was Tuesday. Let me make sure with the kilopascals, I don't use that a lot, so I want to make sure that I'm using the right conversion. Let's see, the conversion table was right, yeah, here. Yeah, I was correct. They have it here in pascals, but when you take the kilo, put the decimal here, it works. Okay, so back to this. We don't have our conversion. This is in millimeters of mercury. They have inches, right? So we need to fix that. Man, this makes it a little bit more complicated. That's okay. That's okay. Now I'm going to make it easier because you will not be encountering any homework problem like this. They do have a conversion here. I saw it. Let me see. where you have the atmospheres in inches of mercury. Let me go ahead and copy that one because I don't really have that one in my list either. Nor do I have that one memorized. 29.92 inches of mercury. Okay. So what I'll say with this one here is this. Because I'm trying to save time for us to cover what I know for sure you need to know for your homework and for the exam, I just copied this conversion here. If I didn't copy this, I'd have to do a manual conversion from 760 millimeters to inches. Okay? But you don't have to do that. If you have the conversion, just use the correct conversion. So I'll start with the first one. 29 psi is my first conversion. Okay, so you find the conversion that has psi in it, right? That will be this first one. Put 14.7 psi. Remember, we're going, these two have to go to kilopascals. 14.7 psi, and then 1 atmosphere right there. Psi cancel. We're not at kilopascals yet. Remember, in dimension analysis, you always have to write where you're going to so you know how far to go, right? We are atmosphere right now, so I need to do one more conversion to get to kilopascals. I'll be using this one next. 1 atmosphere, 101.325 kilopascals, right? And so this first number is now at kilopascals. Let me do the math. 29 times 101.325 divided by 14.7. So now I have 199.89 kilopascals, okay, for my first part. Now remember, I'm going to be adding these two in the end once they're the same unit. Second part, I have 30. I haven't rounded this up or down, but if I was to round this up, it would be 200, which would be one significant figure, so it would be 20.2.00. If I round this up, this would be 2.0 times 10 power, let's see, 122 kilopascals. To the correct significant figure, right? I can't write 2.00 because that would be three significant figures. Yeah, so if I were to round it up right now, I'll write it that way, but I'm not rounding it up yet. 30.09 inches in mercury. I feel like it's making the question a lot more difficult than necessary. I have to look for inches in mercury conversion. That's this one right here. 29.92 inches in mercury. And then that goes with 1 atmosphere, right? So convert that. We got to atmosphere again. To me, atmosphere is like that checkpoint that everybody has to go through, kind of like paying toll when you're going on a highway. Like all of these conversions have this toll spot. You go and check in. That's ATM for you. Now we're at ATM to get to our desired destination for units. 1 ATM, 101.325 kilopascals, and this cancels out, and we have our answer in kilopascals. So now I write 30.09 times 101.325 divided by 29.92, and I have 101.9 kilopascals. Okay, then you go ahead and add these two after that. I'll add it with the first number plus 199.89, and we end up with 301.8 kilopascals. Okay, but the point here was about converting. Since we have converted, now I want to go ahead and spend the remaining time on the other problems, right? So yeah, feel free to go back and watch this part. I wanted to say rewind, but I'm trying to wean myself off of those old words. We don't rewind stuff anymore. We're not watching tapes or DVDs, right? So we don't rewind. You just go back in time and scroll back. Okay, so we're done with this math right here. They go ahead and add it. They get around 300. You want to make sure you know temperature conversions, right? Remember, for temperature, you usually in the gas laws, for temperature, you usually go into Kelvin. So remember, to go to Kelvin, you take your degrees Celsius, add 273.15. Okay, 273.15. Okay, so then we scroll. Oh, we're done with that. We're done with this. We're done with this. I'm going to skip over that for right now. Oh, we go over Charles' law. You want to make sure you know the three gas laws, right? So I see they cover Charles' law here because your lab will be over Charles' law. Charles' law here, they cover what else? Boyle's law, then they cover the combined gas law. Yeah, so the combined gas law. I see that right here. Okay, so let me give you a quick, oh, and they go over Gay-Lussac's law and Avogadro's law. Nice. Okay, so let me give you a quick summary over this before we start doing the math, because the thing in chemistry is you can't do the math, and the math does not make sense if you didn't understand the concept behind it. Okay, so I'm going to go over a quick summary of gas law. Then we'll do the other worksheet because I do have another worksheet. So summary of gas laws. Okay, so I'm going to start with, we're going over Charles' law, and Charles' law talks about volume related to temperature. Okay, we'll go over Boyle's law. Boyle talks about volume related to pressure. Oh, sorry, I'll come back to this page real quick. Hold on. I know I just realized you can't see what I'm writing. I'm trying to make sure I have all these copied down. Talk about Avogadro's, and then I'll show this to you. Avogadro's law. This talks about volume related to number of moles. Then we talk about Gay-Lussac's law, and this talks about volume pressure related to temperature. Okay, so let's go back to my iPad right here, and I have the summary. So make sure you write this summary down. This is the bottom line. Now we're gonna describe these laws in words. This is essentially the bottom line. Okay. I'm gonna go through these. I'm gonna state these laws, talk about them in words, state the law. So when it comes to these laws, you want to be able to, as you're copying this, be able to, number one, state law, predict results, and then number three, use equations to solve unknown. And this is where we're going. This is our plan, okay, with these four gas laws. We're going to, first of all, state the gas law. We will try to predict the results based on what it's saying in the gas law. So the results will have to match the gas law, okay? And then we'll use the equation to solve for the unknown. And the unknown is usually just the one thing that's missing in the gas law, okay? Okay, so we haven't started yet, so I can't have questions just yet, right? Okay, so let's start with gas law, number one, which is Charles' law. First of all, I have to quickly say that when you're looking at these laws, you're not really just looking at that one gas law, because the challenging part, I would say, for a new learner of chemistry, when you're from the outside coming in for the first time and you're not used to how things are in chemistry, it can be overwhelming because sometimes you have a feeling you're learning history while you're learning the content. We're not learning the content apart from the experience of the scientist. In a way, the experience of the scientist is part of what we're learning, not their emotions and stuff, but their logic, their thinking, why they did A and B and C. Because remember, this is chemistry, right? I feel like it was appropriately named. We're trying to solve a mystery. So for us to solve a mystery, we're not just trying to figure out what happened, but why it happened. Anyway, scientists were studying the behaviors of gases. So when they were studying the behavior of gases, they weren't just looking at pressure and temperature and whatever. They were studying all the behaviors. So all four properties, I'll say all four properties of gases were studied. And they noticed that there was some relationship between them. So when we're looking at Charles' law, we are actually looking at four properties. These four properties are, there are four properties and measurements. These are pressure, volume, temperature, and moles. Okay? The moles is essentially just another word for amount of gas. Do we have a lot of gas? Do we have less? So these four properties of gases were being studied at the same time, and scientists noticed, oh, they affect each other. It's hard to look at pressure by itself without considering volume, temperature, and the amount of gas. But then they were saying, well, we want to find a relationship. How does each one influence the other? It's hard to study all of them together. So even though in each experiment, we'll consider all of them to make it easier. And chemists tend to be very particular. We will study two only to study how one influences the other and keep the other two constant. So in all of these laws, you will see that, okay? We're studying only two as we keep the other two constant. So now we're ready for Charles' law. Charles' law, ooh, now I can't spell. Charles' law studies volume versus temperature, okay? When moles and pressure are constant. Okay. Now, the good thing about the curriculum we had at home, we studied science ever since the first day of middle school. So you got so many years to see this. So for me, the first time I'm just following along blindly, like I have no idea where we're going with this. I see it again, kind of towards the later end of middle school. I'm like, wait, I've seen this before. Let me see where it's going this time. Oh, the same place. I see it again in high school. I'm like, wait a minute, I've seen you before, Charles Law. We've been here. Guess where it's going? Same place. I see it in college. I'm like, come on now. Now I know where this is going, right? We got volume versus temperature when moles and pressure are constant. So remember, the other two have to be constant. So we're told when the temperature of a gas is increased, comma, the volume increases. So I need to add something here. This is supposed to also be absolute temperature, not just any temperature. It has to be absolute. Okay. So when the temperature, which is the absolute temperature of a gas, is increased, the volume increases as long as the moles and pressure are constant. Okay. So when the temperature of the gas is increased, the volume of the gas increases as long as the moles and pressure are constant. So what we're looking at here is how is volume and temperature related? Volume goes up, temperature goes up. So what we're saying here is volume is directly proportional to temperature, right? When volume increases, temperature increases, and vice versa. When temperature increases, volume increases, number of moles and pressure are constant. So I just wrote the summary of this, right? But what does this mean? I'm going to work one of these out because of the time I have, just one. Okay? So volume is proportional to temperature, Mathematically, we want to get an equation from this. So you want to be able to recognize this, because sometimes they give you this and they ask you this relationship. When volume increases and temperature increases, what law is that? Then you say, oh, this goes with Charles' law. Okay? But I told you at some point we have to get an equation out of this. We have to use equations. How do we get the equation here? Oh, I also did say predict results, right? Here's essentially the results. If the volume increases, the temperature increases, that will be the result because they're directly proportional. Okay? Now, how do we get the equation out of this? We have to get an equal sign. You replace proportional sign with equal constant. So replace this with this. That's the rules in math. I don't know if y'all cover this in math. The math that we had at home, we cover that. I felt like at home our curriculum was more connected. Here, sometimes I feel like it's disconnected. It takes a while for it to be connected in the higher level, but lower level, the math doesn't connect so much to the science. But when in my country, the math that we did was connected to the science in certain ways and the physics and stuff. So, yeah. So, V, replace the proportional sign with the equal K and then T. So, divide by T, cancel this out. We're trying to solve for K. So, we're told that V over T is K. K here is technically constant. So what does all this math mean? From this relationship here, we can actually get an equation, and the equation is going to be V1 T1 equal V2 T2. Okay, you don't have to go through all this process to work this out, but you have to understand what this means. This means V1, T1, these are from experiment in specific conditions, so we'll call experiment 1. And then when you change the conditions, we have V2, T2, a different experiment, but with the same sample, experiment 2. So V1, T1 goes with experiment 1, V2, T2 goes with experiment 2. So you're taking the same gas sample and then you're subjecting it to maybe like a volume V1, temperature T1, and then you're either changing the temperature, which changes the volume, vice versa. Anyway, if you're asked Charles' law questions, use this equation. So use this equation for Charles' law questions. Okay. For the other ones, I'm going to go through quickly so you can see the trend, and then we'll get the equations. I won't go through this whole step here in details, but I'm just going to kind of go from there and skip over just so you can see how it works out. Okay. So this is the first law, Charles' law. Now I have to go to, I've done this part. I'm going to go to Boyle's law so you can see how that works out. Because you cannot really understand the law without really deriving it. So the next one here is Boyle's law. For Boyle's law, this time we're relating, I'll give the short version of this. Volume is inversely proportional to pressure. When moles and temperature are constant. So I'm giving the simpler version of this. Okay. Volume is inversely. I'm going to say inversely is 1 over P, like that, to pressure. Number of moles and temperature are constant. Remember, we're always looking at P, V, and T. We're relating these two. This remaining two here have to be constant. V equal K 1 over P. So we end up with P1 V1 equal P2 V2. So for Boyle's law, we'll use this equation. On the video, the other video I recorded over the lesson, I go into details. So if you want to see the details, watch that video, right? Remember, you want to make sure you know this relationship here. Know how to state this. So know the statement. Know this part here. Know the relationship where we have proportional. Know this. And then know this. So I'm even telling you what you need to know. Okay? So when we need a Boyle's Law problem, we're going to be looking at this one right here. Now I just finished the second law. When we start working problems, you see how it works out. And then let's see, what was the next one? Avogadro's Law. With Avogadro's Law, once again, the scientists have different names. Since you guys have your notes, you'll be able to look at it. Avogadro's Law. With Avogadro's Law, let me see. Avogadro, we're looking at volume again. So volume is directly proportional to number of moles. Okay? And so if we're looking at V and N, so pressure and temperature are constant. Don't forget the constant parts. It's part of the relationship. So volume proportional with number of moles, P and T are constant. So the equation now ends up with volume equal Kn V1 over N1 equal V2 over N2. And this is Avogadro law. Okay? And then we have Boyle'S law. So just in case they ask you this one here, it wasn't the PowerPoint, so I go over it. We have one more law. Now you're probably thinking these are a lot of laws, so I'll show you an easier way to remember it, because I had to memorize this back in my days. Oh my goodness, I used to walk around pacing a lot. Man, I looked stressed out, but I managed to learn it because I struggle with memorizing. I mean, now you see me producing it like it's nothing, right? It took me a lot to learn this stuff. Boyle'S law, P and T. But let me show you the tricks I use, right? Because I've been there. Boyle'S law. We're looking at pressure and temperature. So pressure is directly proportional to temperature, right? So the other two have to be constant. I'm using P and T. That means N and V were left out. Number of moles and volume are constant. Okay, so pressure is proportional to temperature. That means N and V were left out, so they have to be constant. Some of these laws, if I'm not even using it, I'm able to predict the outcome, because remember, you're measuring two, you're working with two, you're leaving the other two constant. That's kind of how it works, right? Okay, so if this P and T start off like this, both in the numerator position, then they end up one on top of the other like that. So P1, T1 equal P2, T2. And go ahead and look at this at your own time later on slowly so you can see when they're both in numerator, they end up on the top and bottom like that. So that's my equation. Okay, so how do I reconcile all of these? Okay, so we're gonna use something called combined gas laws, and I'm gonna share things that I used to things I did as a teenager. Combined gas law. Remember how I told you I'm not very good at memorizing? I tried to study all this. I really did when I was younger, because we were learning this in middle school, and it was like it wasn't really a good time for me because I was a teenager and I was trying to live that teenage life. And it was hard to combine that with this. So I try to sometimes take shortcuts. When I learned the combined gas laws, I was like, wait, why not just learn the combined gas law instead of learning the individual ones? So I did try to learn the individual ones, but it was hard for me to remember them. So what I did was try to see each of the individuals in the combined gas law. So let me show you what I did, okay? You gotta be, resourceful, y'all. You gotta be resourceful. The yellow color I'm showing you here, this yellow color is Boyle's law. if you just take those two, P1V1 equal P2V2, that's Boyle's law. Okay, and then let me show you a different color. Because I was like, hey, I like this a lot better. Now I knew Boyle's law, I knew Charles' law, I knew them all. It's just the way I used to remember them was I went from combined and then I split them up to get the other ones. And I was like, I can do this. Because all I needed was an anchor to help me remember. The green, this is Charles' law. Okay. So let me color the name too so you can see they kind of go together. The yellow. Yeah, Boyle's law is yellow. Charles' law is green. Let me go with a different color that's not going to be overwhelming. Gray. What have we studied? What else have we studied? Boyle'S law. That's this one here. I'll call that Boyle'S, or let's see. Okay, that will be this one here in gray. And then we also talked about Avogadro's law. Now, normally the combined gas law doesn't have the moles, but I'm like, why not just add the moles and make it a lot easier? So what I usually do, I add the moles in here and then make them all fit. So N1, N2, like that. That way I can even bring in Avogadro's and I don't have to even create a whole other situation, right? So Avogadro's, I'll make it pink because I'm writing over so many colors, right? No, I said pink, not red. Okay, right here. So Avogadro's situation will be this one right here. This right here over this. So you see from the combined gas laws, we can get all these gas laws, Avogadro's. Anyway, that's what I use. I didn't get to use my books in the exam, so I had to memorize all these very quick. Right. So that's what I used. Anyway, now that you understand, remember, the equations will help. So when I wasn't sure, let me be honest with you, when I wasn't sure, I just the combined gas law and then cancel out whatever was not relevant to the question. So if you're struggling, use the combined gas laws, right? So now that I've done this little background exercise, now we can go to the questions. So now we can go back here. We left here. So see proportionality symbol, all that stuff, all the math here. So now we're finally here. Okay. 32, they're saying a gas sample. So I'll do the same thing here and just use the slides. A gas sample occupies, so we got volume, right? The first one here is L. Let me make sure. Oh, okay. let me incorporate you guys a little bit more into this part here. So I'll open that so we can see, make sure. If you don't want to talk, you can just go ahead. I don't mind if you talk, it's a lot easier for me, but if you don't want to talk, just feel free to chat. Right, let me say right here. I don't know if you guys see the message box, but right there. Okay. Okay, so the quick overview. Now we're going to be working on this part here. Where is my question? I have so many screens open. Volume 1. So you see the unit here is liters. So when I'm looking at a question, I have no idea what law is being applied, right? Over here, sometimes they'll say what the law is because you're still learning it, but I go by what's given. I know all questions will have P, V, and T, right? So I'll show you what I'm writing a little bit. Volume 1, I have 5.18 liters, this volume right here. And this volume goes with that pressure. P1 equals 776 torr. And it says, find the volume of the gas so if I already have a volume, they're asking me to find a different volume. The volume I'm looking for is volume 2. Okay, this is what I'm looking for. If the pressure is changed too, so the volume I'm looking for goes with this new pressure, which is 827 torr. 827 torr. Okay, so you see what I told you guys before? A good question in this chapter will mention all 4 measurements. They're telling you here temperature and amount. Remember, amount is moles, remain constant. So we're told in this question is about P and V. The ones that remain constant are number of moles and temperature. So now I can move on to my iPad right there. So I just wrote what I got from the question, right? People usually ask me, well, how do I know which is volume one? You get to assign. You, the one who is working on it, you get to decide what's V1, what's P1. But remember, P1 has to relate to V1. So the P that you select has to go with the V and vice versa. So I look at P1, V1, and then P2, V2. They said N and T are constant. That means your equation should not have N and T. Okay? So what I do here, since I have P1 and V1, I go to the equation that has P1 and V1. Okay? Now let me just show you real quick the trick that I used to do when I was still learning this. Since I had this equation P1 V1 over N1 T1 equal P2 V2 over N2 T2, right? This is when I was still learning this. I used to just use the whole equation for every question like this, blindly, because I was like, I don't know which is which. And I used to have test anxiety. I mean, it was awful. So what I'll do here is, since they said N is constant, that means N1 equal N2, right? And they said T is constant, that means T1 equal T2. Ooh, T2. So that means these down here are the same. Now, I was good in math, so I used my strength to help me survive chemistry. So it's kind of like writing like this. They're not different. So this and this cancel out, this and this cancels out, and it would help me recreate the proper equation I should be using for this. Maybe you're a good memorizer and you guys have your notebook, so it makes it different, right? I had to do all this because I didn't have my notebook, and I feel like that kind of helped me to really navigate through this. This is what we're doing. We have P1, we have V1, right? We have this and this. We're trying to find V2. We're trying to solve for this one here, V2. So in the past, I've asked my students, how do you want to solve it? They told me in the past, rearrange first and then solve. I said, okay. So P1, V1 equal P2, V2. We're going to rearrange. We're trying to get V2 by itself. Why is this still reading? Anyway, to get V2 by itself, divide P2 both sides. Divide P2 both sides. P2, P2 cancels out, right? And then we're left with P1 times V1 divided by P2 equal V2. Okay, now all I need is my numbers. So I'm going to scroll down here so I can get my numbers. P1 is 776 torr. I need to write small. I'm writing so big like I have all this space. 776 torr times V1, 5.18 liters over P2, right? 827. Don't leave out the units. Don't ever leave out the units in chemistry because units really, really make a difference, right? V2. Okay, so let me zoom in. Now that I've written the numbers, I'm good. Don't leave out the units because see how torr and torr cancel out? If those units were not alike, I would know, oh, I need to convert. Torr and torr cancel out. Now I have liters left that did not cancel out. That means my answer will be in liters, the unit that remains. Okay, V2. So mathematically, I will just multiply all the top numbers divided by the bottom. So 776 times 5.18 divided by 827. 4.86. Yeah, that's good. Does anybody else get that? Get the right equation of the 4 that we had and then plug it in there and then solve for the unknown. So make sure you have the right equation, right? So what I'm going to do with the next one, I won't just work it out myself. I want you guys to participate a little bit more because I think I can kind of slow it down just a little bit because I want to make sure that I wanted us to work on the other worksheet, but we may not really have time for that. Okay, but you see how I got this, right? I rearranged my equation, and then of course I plugged in the numbers, and then it worked out this way. So remember, for the equations that you have, make sure you have all the equations here. So real quick, because y'all haven't said anything in a while, for the equations, P1 V1 equal P2 V2. This is Boyle's law. V1 over T1 equal V2 over T2. This is Charles. And then you have V1 over N1 equal V1 over V2 over N2. All the 2's are on the right. What's this one? Avogadro's. And the last one was P and T, right? So that would be P1 over T1 equal P2 over T2. This is Gay-Lussac's. So you want to look at the question and see what's given to you. The question has to have one of these conditions, either this or this or this. Or it could be the combined one. You want to just write down what's given and then what's changing based on what the question says. Any questions about this? Oh, one thing I want to mention here. Temperature has to be, I'll say here, convert to Kelvin. For the questions that have temperature in it, you have to convert to Kelvin. I forgot to mention that. We haven't done a Charles Law question yet anyways. Temperature, convert to Kelvin. In this section here, these laws only work when temperature is in Kelvin. Any questions about this? Okay, so you're picking from either this or this or this or this, or the combined form if the question we're working on asks for more. Okay, so let me see what the next question in the PowerPoint slide says, and then we'll continue. We did this one. Let's see what they got. Oh, 4.86. Ha. Oh yeah, they summarize the laws here. So now I'm moving on to this next one. Oh, the combined gas law. Talked about that. Is this a combined gas law question? I don't know. Let's see. Okay. Says a cylinder in an automobile engine has a volume of, so I'm going to write this down. I'm writing down what's given. Volume of 352 centimeters cubed. The engine takes in air at temperature 21 degrees Celsius and pressure of 0.945 atm. So right now, before I continue, I am going to assume that this volume I got here goes with this temperature and this pressure. But I'm going to keep reading on, then I'll know more. The compression stroke squeezes and heats the gas until the pressure. Okay, so now I have a second pressure. So I'll write next to that P, that's P1. P2 is 4.95 atm. Oh, the temperature also changed. That will be T2, making the first one T1. T2 is 95 degrees Celsius. And they're asking you, what is the final volume of the cylinder? So we're looking for V2. Okay, I don't know. Okay. So I just wrote this stuff down based on what's given to me in the question. Now, as a student, word problems used to scare me and overwhelm me because I'm like, oh my goodness, words. I'm going to get lost in the words. And then by the time I got to grad school, the question didn't have a lot of words. All of a sudden, I was missing words because they were so hard. But I learned with words, word problems, just break it down. Like read one statement at a time. Like read to the first number, try to make sense of that, and then keep reading. And if it's not making sense, read the whole problem and then start again. So I would read over and over, maybe 3 or 4 times until I felt comfortable, understood the purpose of each number. Okay. So it took me having a lot of practice to become a lot more comfortable. So from that question, this is what I got. That these three numbers went together, okay? That means that these go together. So you see how the units match, right? Even though I don't have V2 yet, I know it will have to be centimeter cube because all the units have to match across. This question here has temperature. That means the temperatures have to be converted to Kelvin. Remember I told you these questions usually talk about P, V, and T. So I was given P, I was given T, V, sorry, and T. Nothing about N. So we can assume that N is constant. Because if they wanted to say anything about it, they would have said something about it, right? They didn't just leave N out because they forgot. It's because N is not changing, so N is constant. So here's where I was telling you guys, normally for this, I'll just use the combined equation. You have to actually. But convert the temperature to Kelvin so you don't forget. How do I convert the temperature to Kelvin? We've done this before. What do I do to go from Celsius to Kelvin? What's my equation?
You add 273.15.
Yes, Kelvin is degrees Celsius plus 273.15. Yeah. Okay, so I'm going to do that with this. I don't have a lot of space here, so I'm going to say 21 plus 273.15. Oh, calculator, come on. 0.15. Okay, so this is the same thing as 294. Ooh, I said 4 and I wrote 9.15. Okay, and then let me erase this here. Erase. 95 plus 273.15. This is the same thing as 368.15. Okay, this is Kelvin, this is Kelvin. We need these in Kelvin for the laws to work, or else our answers will be wrong. Okay, since I have P, T, and V, what equation do I use? I'm assuming you guys have these written down, right? I mean, I gave you the individual ones, but you can see if I use this one, I'm only dealing with P and V. What about T? So none of these by themselves will work. You have to use the combined one, right? So you gotta use P1, V1 over T1 equal P2, V2 over T2. Other than that, the rest is just plug and chug. We're trying to solve for what? V2? We're trying to solve for this one right here. So here's the fun part. We're trying to solve for V2, so we have to get V2 by itself. The quickest way to get V2 by itself is by getting rid of P2 and T2. So in math, the shortcut way is to just multiply it by its inverse. So what I mean by that is kind of like dimension analysis. Make sure there's another P2 on the bottom. So if there's a P2 up here, bring another P2 on the bottom. If there's a T2 down here, bring another T2 on the top. Like dimension analysis, right? This is our way to get rid of P2 over T2 in one move. But since we have this equal sign here, whatever you're doing on the right, you have to do on the left. So if we're multiplying the right with T2 over P2, do the same thing to the left. T2 over P2. I don't know what the name of this rule is. I did the math. I learned the math a long time ago. I've forgotten the names of the rules. I don't even think we were taught the names, African schools. Okay, so at least the school I went to, I cannot blame it on all the other schools. Since these match diagonally, right, now I can cancel this and this. Since these match diagonally, I can cancel this and this. So that was strategic on my part. In one move, I got rid of those. So now I'm left with T2, P1, V1 over P2, T1. All I did was just bring all the numerator ones together and then the denominator ones, the bottom ones together, right? Now I have V2. So if I put the numbers in here, I can get V2. So what's T2? T2 is not 95, but 368.15 K times, multiply all numerators, P1, 0.945 ATM, times V1, 352 centimeter cube, over P2, 4.95 ATM, times T1. Where's T1? 294.15 K. Okay? Like before, let's go ahead and cancel out the units before we waste our time doing the math. If the units don't work out and give us what we need, the math is not going to work out, right? K and K cancel out. ATM cancels out. Our answer would be centimeter cubed. Let me check real quick. Centimeter cubed, yes, that means the math will work out. Multiply all the denominator, the numerator, sorry, the up numbers, divide all the bottom numbers, right? So I got 368.15. Oh, it just disappeared. Calculator. Okay, 368.15 times 0.945 times 352 equal, divided by 4.95 divided by 294.15. So I divide all the denominator numbers and I get 84.1 centimeter cubed to be my V2, my wanted volume. Let's see what they say. Oh, sorry, end of slide. Ha, look at that. Oh, they did the math right here. Okay. Okay. Any questions about this method? So just once again, for this part, just like you see me doing in my on my iPad, make sure you write your notes. The way you write your notes, the more organized you are, you write your notes like they're tools for something you're going to be solving in the future, the less apprehensive or nervous you will be. I didn't realize being organized was important. So once I learned that, some people taught me this in school, having your notes organized, highlighting them and saying this is important and you need to know this to solve this problem. It will help you when you're studying, it will help you when you're solving problems, even on the exam. Okay? So, oh, here's when they cover the last two laws. Okay, I was a little concerned we weren't going to have time for my worksheets, but I think we do. Before I go to my worksheets, does anybody have any questions? Okay. Let me go right here then. I think I'm done with this. So with this one right here, well, yeah, my worksheet does have this. We already did, what is it called? A conversion like this last week. So I think I'm fine with that. I want to work this one here because this is different from the one we just worked. Yeah, it's different with the remaining time. Says here, what pressure in ATM, so we have to get our pressure in ATM, is required to compress. So we are looking for a pressure. Let me call it pressure 1 because I have no idea what it is. It says in ATM, is required to compress 1 liter. So we're given okay, is required to compress 1 liter of gas. So I'm assuming this goes with 1 liter of gas. This is what I'm talking about, this kind of question, right? What pressure in atmosphere is required to compress 1 liter of gas at 760? The way this question is written, it looks like the 1 liter of gas goes with 760 to a volume of 50 milliliters. So this question, the way it's written, you have to read the whole question because of just the way it's written. So they're trying to figure out the volume of the gas. I'll start with this. The volume of the gas goes from 1 liter to 50 milliliter. So 1 liter is a huge volume. 50 milliliters is a small volume. So they're asking you what pressure can you apply to 1 liter to take us to 50 milliliters. So from looking at this, I'm thinking that the volume they gave us in the beginning, the 1.00 liters, actually goes with the pressure of 760 milliliters. Okay, so this is one of those questions where you really have to know the law to know what numbers goes where. Okay, it's not so simple. Oh, 50.0. So I'm going to confirm it by using the law in just a moment here, and I'll show you how. Okay, the law says the volume and the pressure are inversely proportional. Okay, that means that if we go from, if the volume is low, the pressure has to be high. Okay, if the volume is large, the pressure has to be low. So we're going from a large volume to a small volume. So that means if we're trying to compress, we're going from, oops, I didn't finish writing this properly. Why did I stop? Okay, this is supposed to be millimeters of mercury, right? We're going from this pressure here, that's big, atmospheric pressure, to a smaller pressure. So this actually goes together, right? Large volume to small volume. So this is supposed to be V2, V1. So this has to be the larger pressure to the smaller pressure. Hold on a second. Let me read this over again, because as I'm reading this, I'm like, okay, yeah, the 1 liter volume is at 760. So yeah, it does say here it is at that. So because the more I read into this, I'm like, wait, am I overthinking this? They do say it is at. So the first encounter of the volume is 1 liter, and the pressure is 760 millimeters of mercury. So let me write this units properly. Yeah. Okay, so let's see what we have going on here. What is pressure 1? So you can do it that way. You could also assign P1 to be 760 millimeters of mercury, and then V1 to be 1 liter. They just have to go together, right? So in this case here, I realize I don't really have a lot of space. Let me write this smaller because I'm running out of space. P1 is what we're looking for. It has to be in atmosphere. V1 is given to us as 50 milliliters. P2 is 760 millimeters of mercury. V2 is 1.00 liters. Okay. So going with the question, remember these go together because the 1 liter of gas is at 760 millimeters of pressure. Okay. Here's the issue with this question. The units of pressure don't match. Because the units of pressure don't match, I can't even go to the question just yet until I convert the pressure, right? So here, I have to convert, since our desired pressure is in atmosphere, I have to convert this to atmosphere. So right here, 1 atmosphere is 760 millimeters of mercury. Okay? The units cancel out, but I end up with just 1 atmosphere. So in my problem, when I'm solving this, P1 V1 is the equation I'm going to use. P2 V2. We're trying to solve for P1, so divide both sides by V2. V2. Sorry, divide both sides by V1 because we're usually trying to solve for something else. Now my mind is kind of caught up on something else. So hold on. V1, divide both sides by V1 right there. V1, V1, and we end up with P1 is equal to P2 is 1 atmosphere. V2 is 1 liter. Oh, I just noticed something. I forgot to convert the milliliter to liter. My bad. Let me do it right here. That's the reason why you don't drop off units. Because if you drop off units, you forget to see that things haven't been converted, right? This question is not so easy. From the conversion sheet, which I don't have with me right now, 1 liter is 1,000 milliliters. So I have to convert this to liters. I have 50 divided by 1,000. So this ends up being 0.05 liters. Okay, so now I can see V1 is 0.05 liters. That's why units are so important, right? Had I not put the units here, I would have missed the fact that this didn't get converted. So 50 divided by 1,000, I got that. So now I take the top numbers. 1 times 1, the units will cancel out. My answer will be an ATM. So it's 1 divided by the answer I just got. So the pressure is going to be 20 ATM. Okay? So now it kind of makes sense, right? The pressure is 20 ATM. So in other words, when the pressure is 20 ATM, the volume is 0.05 liters. This is a volume and pressure relationship. When the pressure is 1 atmosphere, the volume is 1.00 liters. So when the pressure is high, the volume is low. When the pressure is low, the volume is high, which confirms the law, right? Once again, if you focus on this part here, it shows you what the liters goes with, which pressure the liters goes with. Let me see, volume temperature. I'm trying to see, I'll work one more and then I'll let you go. Which one do I want to work on? So we have a volume here. You got temperature. Oh, we're looking for a new volume. Let me work on number 3 because we've done the combined one before. I'll work on number 3 and that'll be the last thing we work on. A 471 milliliter sample of neon is collected. So we have volume 1 as 471 milliliters of neon is collected at temperature 1 is 44 degrees Celsius. I'll convert that to 273.15 to Kelvin. Oh, I'll just write it like this, 317.15, right, Kelvin. You add 273.15. So I'm right here, I've gotten these two numbers. Assuming the pressure remains constant, yes. What would be the volume? So we're looking for volume 2 in milliliters of neon at a temperature 2 is 125 degrees Celsius. This is the same thing as 125 plus 273.15 to convert to Kelvin. We get 398.15. Okay, so V1 over T1 equal V2 over T2. We're trying to solve for what? We're trying to solve for V2. So multiply by the inverse, multiply by T2 both sides to get V by itself, V2, multiply that, and we end up with T2 times V1 over T1 equal V2. So what is T2? T2 is this number here, 398.15 K, I forgot to put the K here, times, that's T2. What's V1? 471 ml. I don't have a lot of room. Divided by T1, 317.15 K. There. Okay? And this is equal to V2. The K and the K cancel out, and our answer should be milliliters. I was looking for, yeah, so we're in the right track, right? So now, 398.15, I already have that in my calculator, times 471 divided by 317.15. I get V2 as equal to 591.3 milliliters. And that will be our new volume, okay? So just make sure you convert temperature to Kelvin and then make sure the other units match, right? In this case, these volumes matched, the temperature units matched. Over here, of course, I figured this out last minute. I had to convert the volumes to match. I had to make sure the pressures matched. And so make sure the units match. So that should be it. This is all I have for today. Do you have any questions?
No, that's it. Thank you.
Okay, yeah. Go ahead and work on your homework. That way, if you have any questions, you can just go ahead and email me.
All right, I will. Thank you.
Okay. Okay, you're welcome. Have a nice day.
You too. Bye.
Bye.